For the first time in more than half a century, human beings climbed into a spacecraft and flew toward the moon. Not to land, not yet, but to go further into deep space than any crewed vehicle had ventured since the final Apollo mission left lunar orbit in December of 1972. That mission was Artemis II, and everything about it was enormous. The rocket was enormous. The spacecraft was enormous. The ambition behind it was enormous, and the price tag was enormous. It cost over $4 billion for a single launch. $4 billion to send 4 astronauts on a 10-day flight that looped around the moon and brought them home safely. That number has sparked fierce arguments in living rooms, comment sections, congressional hearings, and aerospace conference rooms ever since NASA began seriously developing the program. Some people hear that figure and feel a surge of national pride, the idea that America is once again reaching beyond everything it has already achieved. Other people hear it and feel something closer to fury, questioning why that money was not spent on hospitals, schools, bridges, or any of the 1,000 things on Earth that desperately need attention. Both reactions make sense. Both reactions miss something important. The real question is not simply whether $4 billion is a lot of money. It obviously is. The real question is what that $4 billion actually bought, what it will continue to buy in the years and decades ahead, and whether any of that return justifies the investment. And to answer that question honestly, you have to understand exactly what Artemis II was, why it was designed the way it was, who built it, who paid for it, and what it means for humanity's future in space. This is not a simple story. There are parts of this program that are genuinely inspiring, genuinely historic, and genuinely important. There are also parts of it that represent some of the most wasteful, bureaucratically bloated spending in the history of spaceflight. Understanding the full picture requires looking at both with complete honesty. So let us start at the beginning, with the mission itself and the vehicle that carried it into space. Because before you can evaluate whether something was worth the money, you need to understand exactly what you are evaluating. Artemis II launched atop NASA's Space Launch System, commonly known as the SLS. This is the most powerful rocket currently flying anywhere on Earth. When fully assembled and ready to go, it stands about 322 feet tall, which puts it roughly in the same height class as the Saturn V rocket that carried Apollo astronauts to the moon more than 50 years ago. The SLS produces approximately 8.8 million pounds of thrust at liftoff, making it genuinely one of the most impressive machines ever built by human hands. The raw engineering involved in getting that thing off the ground is staggering, and nobody who watched the launch could honestly argue otherwise. Sitting at the top of the SLS was the Orion crew capsule, built by Lockheed Martin. Orion is specifically designed for deep space travel. It is not the kind of spacecraft you use to ferry crew members to the International Space Station, which sits only about 250 miles above Earth. Orion is built for journeys that take it tens of thousands of miles further out, into an environment where Earth's protective magnetic field offers no shelter, where radiation from deep space hits the crew much harder, and where the spacecraft has to survive a return to Earth at speeds approaching 25,000 miles per hour. That re-entry speed is not a small technical detail. It is one of the most important things to understand about why Orion exists, and why nothing else currently flying can replace it for this specific job. When a spacecraft returns from the moon, it is travelling roughly 40% faster than a spacecraft returning from the International Space Station. That difference in speed translates directly into a difference in heat. The thermal forces involved in a lunar return are dramatically more intense, and the heat shield protecting the crew has to survive accordingly. Orion's heat shield, which is the largest of its kind ever built, was specifically engineered to handle those conditions. The crew of Artemis II, Commander Reed Wiseman, pilot Victor Glover, mission specialist Christina Koss, and Canadian Space Agency astronaut Jeremy Hansen rode inside that capsule for 10 days, swinging around the moon on a trajectory that took them roughly 4,600 miles beyond the lunar far side, further from Earth than any human beings had ever travelled. That is what $4 billion bought in terms of the hardware itself. But the hardware is only one piece of the financial picture, and honestly, it is not even the most important piece when you're trying to understand what this mission actually cost the American public. The SLS rocket costs approximately $2 billion per launch, just for the rocket itself. The Orion spacecraft adds additional costs on top of that. When you combine everything involved in actually executing a launch, the mission operations, the ground systems, the personnel, the testing and preparation, you arrive at a total per-launch cost that independent analysts and NASA's own Inspector General have consistently placed at over $4 billion per flight. That is the single mission cost. But the SLS and Orion did not materialize out of thin air for this one flight. They were developed over more than a decade, which means the development costs need to be factored in as well. And when you do that, the numbers become significantly larger. NASA's Inspector General has estimated that the total cost of the Artemis program through the year 2025 is approximately $93 billion. Let that number settle for a moment. $93 billion. That is not the cost of a single mission. That is the accumulated cost of developing the rocket, developing the spacecraft, developing the ground systems and launch infrastructure at Kennedy Space Center, funding the Gateway Lunar Space Station project, developing the lunar landers, running the program office, and covering all of the testing, redesign, delays, and overruns that come with developing the most complex human spaceflight system in history. The vast majority of this funding comes from the United States federal budget, which means it comes from American taxpayers. NASA does not generate its own revenue. Every dollar it spends has been appropriated by Congress from the federal treasury. That is simply the reality of how the agency operates. It is a public institution funded by the public. Now, where does that money actually go once it leaves NASA? It flows primarily through government contracts to a relatively small number of major aerospace corporations. Boeing holds the contract to build the SLS core stage, which is the central body of the rocket. Northrop Grumman builds the solid rocket boosters, the two large white cylinders that strap onto the sides of the rocket and provide the initial thrust at liftoff. Lockheed Martin is responsible for the Orion crew capsule. These are among the largest aerospace and defense contractors in the world, and the Artemis program represents a significant revenue stream for all three of them. International partners also contribute to the mission, though their financial contributions are considerably smaller than what the United States provides. The European Space Agency built the service module attached to the Orion capsule, which is the section responsible for propulsion, power, and providing consumables like water and oxygen to the crew during the flight. The Canadian Space Agency contributed to various systems and, critically, provided one of the 4 crew members. Jeremy Hansen became the first Canadian to fly beyond low Earth orbit, which represented a meaningful milestone for Canada's space program and reflected the kind of international cooperation that the broader Artemis framework is designed to encourage. But here is where the conversation about cost has to become genuinely honest, because there are real criticisms of how this program is structured that simply cannot be brushed aside in the name of enthusiasm. The SLS rocket is entirely expendable. Every single component is used once and destroyed. The core stage, worth roughly $2 billion, splashes into the ocean after each launch and is never recovered or reused. This is fundamentally different from how modern commercial rockets are increasingly designed to operate. SpaceX has demonstrated with both the Falcon 9 and the Falcon Heavy that rocket boosters can be landed and reflown many times, dramatically reducing the cost per launch. The Falcon 9, for comparison, can deliver a comparable mass to orbit for somewhere around $60 to $70 million per flight, a fraction of what the SLS costs. The SLS also relies heavily on legacy technology. The main engines that power its core stage are RS-25 engines that were originally designed for the Space Shuttle program, which flew its final mission in 2011. These engines were among the most sophisticated cryogenic engines ever built, and they remain genuinely impressive pieces of engineering. But they were designed for a system where they would be recovered and reused. Attached to the SLS core stage, they splash into the ocean along with everything else, which means each set of engines is essentially thrown away after a single use. Space policy analysts and aerospace journalists have been raising these concerns loudly for years. Some have called the SLS a jobs program more than a space program, arguing that its primary purpose is to distribute federal contracts across the right congressional districts rather than to develop the most efficient path back to the moon. That is a harsh characterization, but it reflects a genuine structural problem. The political reality of large government aerospace programs is that the contractors who build them have significant lobbying power, and members of Congress whose districts benefit from the contracts have strong incentives to protect them. Changing course, even when changing course would obviously produce better outcomes, is politically difficult in that environment. NASA's Inspector General and multiple independent analysts have urged the agency to transition away from the SLS as quickly as possible and move toward commercially developed, reusable rockets. SpaceX's Starship, which is designed to be fully and rapidly reusable, could theoretically perform the same mission profiles as the SLS at a fraction of the cost if it reaches full operational capability. Blue Origin's New Glenn is another commercially developed heavy-lift rocket that represents a potentially more cost-effective path forward. But here is the uncomfortable reality that critics of the SLS sometimes gloss over. For the specific task of returning humans from the Moon, the Orion capsule is currently the only crewed spacecraft in existence that has been tested and proven capable of surviving the re-entry conditions involved. No commercial crew vehicle currently flying was designed for lunar return velocities. They are built for low Earth orbit operations. Replacing Orion for lunar return would require developing a new vehicle capable of surviving those conditions, which takes time and money. For the immediate near-term missions, including Artemis II, NASA was effectively using the only hardware available that could actually do the job. So then the question becomes, was it worth it? Was $4 billion of taxpayer money embedded in a $93 billion program worth spending to send 4 astronauts on a 10-day flight around the Moon? The scientific case is more compelling than many people realize, and it depends on something that often gets lost in the hardware-focused conversation. It depends on what human observers can actually see and do in space that robotic probes simply cannot replicate. Robots are extraordinary tools. Rovers like Curiosity and Perseverance have transformed our understanding of Mars. Telescopes like the James Webb have revealed galaxies that formed just a few 100 million years after the Big Bang. Remote sensing and automated science have advanced enormously in recent decades. But there are things a human brain does during direct observation that no robotic system has yet managed to replicate. The human eye, combined with the processing power of the human brain, functions as an extraordinarily sophisticated scientific instrument. When an astronaut looks at a lunar landscape, they are performing real-time stereoscopic analysis, interpreting subtle color variations, noticing anomalies, and making judgments about geological morphology that take years to extract from flat digital images. The human eye is particularly sensitive to subtle differences in hue, the kind of difference that might distinguish volcanic deposits from impact ejecta, or identify mineral-rich zones that a programmed sensor might overlook because nobody told it to look for that specific signature. The Artemis II crew was given specific observation tasks that were designed to take full advantage of this capability. One of them involved watching the lunar terminator, the boundary between the sunlit and shadowed regions of the Moon, to look for evidence of electrostatically lofted dust. There is a long-standing scientific question about whether the Moon's surface experiences a phenomenon where fine dust particles become electrostatically charged near the boundary between sunlit and shadowed regions and actually levitate above the surface. This would have significant implications for future surface operations and for understanding how the Moon's surface evolves over time. Human observation during a close lunar flyby is one of the best ways to gather data on this phenomenon, because the human eye can detect subtle, visual phenomena at the terminator that automated sensors might simply not be calibrated to find. The crew also had a direct view of some of the Moon's most scientifically significant features, including the Orientale Basin and the South Pole Aitken Basin. These are among the largest and most ancient impact structures in the inner solar system. The South Pole Aitken Basin, in particular, is a colossal depression near the Moon's south pole that is roughly 1,600 miles across and more than 5 miles deep in places. Understanding its formation history is directly relevant to interpreting the samples that future Artemis surface missions will bring back from the lunar South Pole region. Human observation of these features from close range, with the ability to note subtle details in real time, adds context to everything the robotic instruments measure. Looking back at Earth from lunar distances also provides scientific value. The crew documented global-scale atmospheric and oceanic systems, observed changes in vegetation and forest cover, and recorded the spread of artificial light from cities across the continents. These observations, made from the perspective of someone who has actually stood on Earth and can compare what they are seeing from deep space to their lived experience of the planet's surface, carry a qualitative richness that no automated mission can fully replicate. And then there is the engineering and systems validation dimension, which is arguably the most important scientific justification of the entire mission. Artemis II was not just a science flight, it was a test flight, and what it was testing was the entire architecture of deep space human exploration. Every system aboard Orion, the life support, the propulsion, the navigation, the communication arrays, the emergency procedures, the manual piloting capability, all of it had to perform in the actual environment of deep space, not in a simulation, not in a testing chamber, but in the real environment where cosmic radiation hits the craft, where the temperature differential between the sunlit and shadowed sides of the spacecraft creates thermal stress, where the communication delay from Earth starts to matter in a real operational sense. Getting human beings to and from the Moon, and eventually beyond, requires hardware that has actually been tested in the conditions where it will be used. Artemis II was that test. It validated systems that will carry astronauts to the lunar surface on Artemis III, and that will eventually form the foundation of crewed missions to Mars. The value of that validation is not easily expressed in a single dollar figure, but it is real, and it is significant. The economic argument for the Artemis program extends well beyond the immediate returns of the mission itself, and it connects to trends in the global space economy that are reshaping multiple industries simultaneously. A joint report from the World Economic Forum and McKinsey & Company projected that the global space economy, which was worth approximately $630 billion in 2023, is on track to grow to $1.8 trillion by 2035. That is an extraordinary growth trajectory, and it is being driven by a combination of satellite communications, Earth observation services, space tourism, lunar resource development, and the infrastructure that supports all of those activities. The Artemis program sits at the center of this expanding economy in a specific and important way. Every successful crewed mission that validates the Orion spacecraft and demonstrates that deep space operations are feasible and repeatable sends a signal to commercial investors that the infrastructure for lunar operations is real and is being built. That signal unlocks investment in ways that are difficult to trace directly, but are genuinely significant. When private companies see a sustained government commitment to deep space operations, they are more willing to invest in the complementary technologies, the propellants, the cargo delivery systems, the habitat modules, the in-situ resource utilization equipment that will eventually make lunar operations commercially viable. The Artemis Accords add a geopolitical dimension to this economic story. As of the time of writing, more than 50 nations have signed the Artemis Accords, a set of principles that establish norms for peaceful, transparent, and cooperative use of space resources. These accords do not have the force of international law, but they function as a diplomatic framework, a signal of alignment with a particular vision of how space exploration and resource utilization should work. The United States wrote those accords and leads the coalition of signatories. That is not a small thing in a world where China is simultaneously developing its own lunar program and has explicitly stated its goal of landing taikonauts on the Moon before 2030. The lunar South Pole, which is the target of Artemis III and subsequent surface missions, contains water ice in permanently shadowed craters. Water ice in space is not just water, it is rocket fuel. It can be broken down into hydrogen and oxygen, which are the propellants used by a wide range of spacecraft engines. A nation that establishes a sustainable presence at the lunar South Pole and develops the technology to extract and process that water ice is positioned to dominate space transportation economics for decades. The water ice at the lunar poles is potentially the most strategically significant resource in the inner solar system. And establishing a presence there is not simply a scientific ambition, it is a strategic one. When people debate whether Artemis II was worth the money, they sometimes forget to ask who the alternative would be. If the United States pulls back from lunar exploration, the space at the top of that field does not stay empty. It gets filled by whoever is willing to show up. China has been consistently and methodically developing its space capabilities. Russia and China have signed a memorandum of understanding to develop a joint lunar research station. The geopolitical case for maintaining American leadership in deep space exploration is real, and it is backed by history. Leadership in space translates to leverage in diplomatic relationships, advantage in attracting scientific talent, and credibility in shaping the rules that will govern how space resources are eventually extracted and used. Now, let us talk about the number that has circulated most widely among people trying to make the cost of Artemis II feel tangible. If you take the $4 billion mission cost and divide it among the roughly 325 million people in the United States, each person's share is approximately $12.30 for the full mission. If you then spread that cost across the roughly 3 years between the Artemis I test flight and the Artemis II crewed mission, the per-person annual cost is somewhere around $4. That works out to slightly more than a penny a day per American citizen. A penny a day. That is what each individual American paid, on average, for the first crewed deep space mission in more than 50 years. For the first woman and first person of color to fly beyond low Earth orbit on a lunar trajectory. For 10 days of live broadcasts that drew tens of millions of viewers and inspired a generation of young people to think about careers in science, engineering, medicine, and technology. Space advocacy organizations and ordinary citizens have pointed out repeatedly that this investment sits in remarkable contrast to how much the United States spends on other things. The annual defense budget approaches $900 billion. Studies have estimated that extended military operations in various overseas theaters have cost somewhere between $28 and $33 billion over periods of 39 days or less. You can disagree about whether those military expenditures were necessary or wise, but the comparison is worth sitting with.